Math and Beats. We're here to talk about two-sided infinite limits in a formal way. So let's take a look. All right, what is a two-sided infinite limit by definition? We write this right here. Limit as x goes to some number c of the function f of x is infinity, provided that for any number n that is positive, there exists some delta also positive, so that the function is bigger than this number n whenever the magnitude of x minus c is less than delta and positive. So in other words, what is that saying? It is saying that for the deleted neighborhood of x around c, no matter how tiny of a distance you move left or right, this function f is always bigger than some number n, whatever that might be. So you kind of think about pictorially, what would that look like? Something like this. So here's your deleted neighborhood of x around c, delta neighborhood down here below, as we can see. Move to the left delta units from c and move to the right delta units from c. And then there exists, this relationship between some number n that we pick. So no matter which n we pick in relationship to delta, no matter how far away I am from this number c in this delta deleted neighborhood, then it follows that this function right here, you can see the curve in black, that curve is always bigger than this number n regardless. So really what that's saying is that, no matter whatever deleted neighborhood we pick around this number c, then we can find some number, n as we call it, that's positive, so that the function is always bigger than that number n. In other words, f is going to get large without bounds as we get near c, because the closer we get to c, the bigger the function gets, and then we can find the relationship between n and delta, provided it exists, if this is what's going on. Then, if all of this is true, we would write limit as x goes to c of f of x is infinity. We'll take a look at an example here. We would like to prove something right here. We're going to take a look at this function. F of x is 1 divided by quantity x minus 3 squared. And we're going to prove that the limit as x goes to 3 here of the function is infinity. So the graph's going to look very similar to the graph we saw right above because of the nature of the function being a rational function, and even more specifically, it is just a horizontal shift of the reciprocal square function. Now, in order to prove this statement, very similar to how we showed how to prove a limit that is some real number for some function, we're going to have to find this relationship now with delta and n. So we got to find some delta bigger than 0 that satisfies the definition that we need. And hence, there's got to be this relationship between delta and n, similar to how there would be a relationship with delta and epsilon in the real valued number limit case. So, in order to find this delta, we're just going to solve the inequality f of x bigger than n, because that has got to be something that always happens regardless of this relationship that we have between delta and n. All right, so we go ahead and solve that. F of x bigger than n, we're going to find this n. Well, that's the same thing as saying 1 over x minus 3 quantity squared is bigger than n. And then we're going to solve that. If we divide both sides by n and multiply both sides by x minus 3 squared, we get the next statement. 1 over n is greater than x minus 3 squared, noting that that's not going to mess with the inequality symbol since n is assumed to be positive, and note that x minus 3 squared is positive as well for values of x not equal to 3. So it's not going to switch the inequality symbol. So we go ahead and solve that for n. That means 1 over square root of n, taking the square root of both sides of the inequality there, has got to be bigger than magnitude x minus 3 because of the fact that n is assumed to be positive, and therefore we don't have to really worry about the other inequality symbol as well. So therefore we should pick this delta to be 1 over the square root of n. So now we'll write out the proof. The proof, well, just state the proof based on the n we found. Let's suppose we have some n bigger than 0, and let's let delta be 1 over square root n, which of course is also going to be positive. So then, if we consider the inequality 0 less than magnitude x minus 3 less than delta, well, delta is equal to 1 over the square root n, and that says, therefore, we just square both sides. We get x minus 3 squared is less than 1 over n. Hence, n must be less than 1 over x minus 3 quantity squared, which is the same thing as saying that f of x bigger than n. So, it shows that as long as delta is in this neighborhood right here, around 3, and we let delta equal 1 over square root n, then it always is true that the function is bigger than n. The n. Hence, what it shows, we'll write it out one last time in symbols, quantifiers. For all n bigger than 0, there exists this delta, so that when we have an delta neighborhood, a deleted neighborhood around x is 3 of radius delta, if we let delta equal 1 over the square root n, then the function f of x equal to 1 over quantity x minus 3 squared will always be bigger than n. And therefore, limit x goes to 3 of the function f of x equals infinity by definition. So as you can see, the process is very similar to the one in which you prove a limit that is a real number, trying to find the relationship between epsilon and delta using the definition. And in this case, for a two-sided infinite limit, we try to find an n relationship with the delta such that the definition is also satisfied. So that's like a little introduction to what this is and how you could prove such a situation. And that's the end. All right. Show it video. Now show it beat. Math and beats. Light